Log on, tune in, find out. Another good idea from Cambridge.
Today's seminar, we have Vladislav Panferov from University of California. What is California State University at Northridge, please.
Thank you. I hope this thing is working. Okay, so first let me thank the organizers, Jose in particular, for the invitation. Very nice to be here. So the title may sound a little so obscure. So I will explain what Vicsek dynamics is. But so this is related to the area which has gained popularity recently. So this goes under the name of flocking, swarming, biological aggregation, self-organization in biological systems. So this is all about this topic. And so here is the basic. So before I go on, so let me mention so that this is a joint work with Alicia Barbaro from UCLA, and with Pierre Digon from Toulouse. So and this is a work in progress. So which is progressing at the current time. So the talk will not be completely polished. Okay, so this is how it works. So the Vicsek model. So Vicsek is a Hungarian physicist. So he wrote a paper in 1995, which became very popular and so started the whole field of of motion of self-propelled particles. So basically the setting is very simple. So we look at the system of n particles, so which are so just points. So each particle has a velocity. So say this is xi, this is vi. So all the particles move with velocity that is 1 in magnitude. So vi absolute value is 1. So this can be thought of a situation that applies to living organisms. So when we have, for example, birds flying or fish swimming. So the simplest approximation of a motion so would be that that each individual tends to keep constant speed. So this is a certain this is a certain approximation. So this is a simplest version, what is sometimes called as active matter, or so something that applies to motion of animals. Okay, and so the dynamics works in the following way. So each particle looks in a neighborhood. So typically, so let's say a neighborhood is a circle, and so it picks the neighbors in the neighborhood based on the radius. So I will reserve the symbol epsilon for the range of interaction. So eventually this epsilon will go to 0. But so on the first slide, epsilon equals 1. So far everybody is interacting with its neighbors within a zone of finite radius. Okay, and the interaction works in the following way. So there is a kernel K, which I call alignment kernel, and so the alignment. So the simplest situation would be that the alignment kernel is an indicator function of a ball, or a circle of radius epsilon, or some indicator function for a ring. I'll show some pictures about that later on. And so if a particle J is within the zone. The support of K is the zone of alignment. So then the average velocity is Vj over the alignment zone. So this is the term that tells that particles tend to look around within the radius and so align velocities with the neighbors. Okay. So this is another contribution to the interaction, which is the repulsive attractive force. So I write it in the form of a gradient of a potential. So the examples that I will be looking at, so this will be a potential force, but it's not really it's not really a potential force in the regular sense. So basically, so this is so V. I'll put a picture on. So I'll show a picture later on. So typically, a V will have an attractive and repulsive part, and it will be so a potential with finite range. And so I put epsilon to indicate the range of the potential. And to account for a certain error that is committed by particles that try to follow this dynamics, so people put a stochastic term into here. So theta is a certain coefficient that could be related to temperature, and psi I is a random variable. So in the time continuous version, one could think of Brownian motion. Okay, but so for this talk, I will neglect the stochastic aspect altogether, and I will look at the corresponding deterministic dynamics. And well, so deterministic dynamics is sufficiently interesting to make a talk out of it. Yeah, and so I forgot to mention the most important thing. So since all the velocities are absolute value 1, magnitude 1, so in order to keep in order to account for this fact, I normalize. So I compute the interaction and then I divide by the norm of interaction. So I write this as normalize. So this quantity. So this normalize is simply the operation of making a vector a unit vector. Okay, so this is the Vicsek model. So here is the reference to the Vicsek model. So there is a paper of 1995 in PRL, and so there are many papers. So after that, so there is a whole literature. So the interesting point about the Vicsek model is that it displays an interesting phase transition. So there are two regimes in this system. One is when particles align and prefer to move with basically one velocity, and again, so this is concerning the system with the noise. So if the noise is sufficiently if the parameter in front of the noise is sufficiently small, then everybody aligns. And then the other regime is when the noise is sufficiently strong, or if the density is sufficiently high, so there is a relation between the parameters. So then the system prefers the disordered state, which is like a diffusion. So the random part dominates. Okay, and so there is an interesting non-equilibrium phase transition, which is hard to capture in the mean field model. I will say a few words about that. So which is part of the reason that the physics community is interested in this, and this model also has biological implications, which I will mention. So there are some papers, a large literature, so studying flocking birds, schooling fish, swarms of locusts. Well, ants are not really related to this, but I mentioned them anyway because they're animals. And so papers related to motion of fish. So there is a model by Aoki, which I will also describe, and so studies by by many groups of biologists. So there is a work of Kazin, which is also and co-authors, which is also related to these models. So I mentioned the work of Björn Birner and so my collaborator Alicia Barbara and her collaborators so about these models. And again, so I'll provide some details later on. So basically, so these are this is an illustration. So this is not exactly what I will be able to describe with this type of particle systems, but just to illustrate that so fish in the ocean, for example, so swim in an organized manner. So they can perform very complicated functions. So acting as a whole. So for example, avoiding a predator. So a school of fish. So without obvious leader, and without external stimuli, can create a complicated pattern and avoid a predator, for example. And well, just so generally, so these are interesting phenomena, and one can think of how to describe this phenomena with sort of a simple and minimalistic models. Okay. So just to mention a few things about fish schools. So the applications that I have in mind are actually relate to the situations when we have a lot of fish. So when we're looking at pelagic fish, so in the free ocean, There are huge masses of them. So depending on the species, so they could be millions, and up to 10 to the 10 is the estimated stock size of certain small types of fish. So fish schools, as I mentioned, behave as a whole without obvious leader. So they're very efficient in propagating information about environment, predators, and so on. Okay, so this is to refer to a work that was done by biologists. So this is from the work by Barbara Einerson-Burder and so other people. So the problem that they were modeling is the motion of a certain pelagic fish, a capelin, which is a small fish that lives in the northern Atlantic, which performs it has a rather complicated life cycle. So they are born in the south of Iceland, and then they migrate north to feed. They spend a lot of time in the northern waters, and then they perform a spawning migration to the south of Iceland. So this is the picture of Iceland, and so these are the data from acoustic surveys that were done over many years. So there are huge masses of fish which so aggregate and so form large schools or shoals, and so in the period of migration they perform. So this is a picture of January, and this is a picture of February. Sorry, this is October, and this is January, something. So they move from the northern area towards south, and then they go around the island, and then they come to the shore of the south, and they spawn and they die. So it's a interesting phenomenon, and so these people did large scale computational studies using as a particular ingredient the model that I was describing. So with particles moving with speed 1, and so they were able to capture certain things about the dynamics. So in particular, they were able to make prediction based on using these models and so data about the environment. Okay, so just to mention that models like this can have some practical value. Okay, and well, so this part I'll just skip. So basically, the starting point of many studies is this picture. So we look at so in the middle there is a fish. So the way so this is a model that is used in biological literature. Which is based on the following principle. So if other fish are too close to this one, so there is a certain zone of repulsion, and then so if the fish sees a neighbor in this zone, it tries to adjust its trajectory so that to avoid the neighbor. Okay, so then so if there are no fish in the zone of repulsion, they pay attention to the zone of orientation. So if there are fish in this zone, they try to align their velocities with them. And so finally, if the fish is feeling lonely, it tries to get attracted to the fish which is further away in the zone of attraction. Okay, and so this three-zone picture can be represented in terms of a potential of interaction in the following way. So so I introduce. So if you introduce a kernel k, which is so this is a radial function. So it is constant. Well, let's say 1 or certain preferred value in this region, which forms a ring. So then this means that in the alignment zone, the fish align their velocities to their neighbors. Okay, and so this is a picture of a potential which corresponds to the three-zone situation. So if I'm too close, so this provides a repulsive force. So then here there is no force, and then here I have an attractive force. So just to have a caricature of what we can try to use in this model. Okay. Okay, I will mention this continuous time version of the Vicsek model, which is like this. So the model that I formulated in the beginning was formulated as a discrete time stepping algorithm. So fish align their velocities at discrete time step, and the whole system evolves as a discrete time system. So in order to study mean field models, it is more convenient to have things continuous in time. And so one possible model that is related to this is like this. So basically we could think of rewriting the rule for updating velocities in a certain form so that it is convenient for the time continuous version. So if you write it in this form, so this is a finite difference which reminds us of a derivative. We could think of replacing this by a derivative. And in this form, this is a projection onto a direction perpendicular to a velocity. So n plus 1/2 is a certain intermediate moment for the velocity. Well, and then replacing a finite difference in this case by a derivative gives us a model of this type. So this is similar to a Newton's law. So particle x moves with velocity v, and velocity is adjusted in such a way that the particle prefers this average velocity, so vi bar, which is then projected into the direction perpendicular to vi to keep the evolution so that the velocity remains absolute value 1 or length 1. Okay, so and so for this model there's been a lot of work. So in the paper by Digon and Sebastian Monch, so they studied. So they obtained a kinetic Vladislav type equation. So they computed homogeneous steady states and provided a formal derivation of the hydrodynamic limit. So I will talk a little bit about this approach for a related model. Further work compared the particle solutions with solutions of the macroscopic equations. So the macroscopic equations that they obtain in the hydrodynamic limit are a certain hyperbolic system which has some interesting properties. The model that was introduced in that paper doesn't display the phase transition. So when you formulate a mean field model, then with the constant rate as I described on the previous slide, then there is no phase transition in the spatially homogeneous setting. But if one modifies the model to make the density to make the rate density dependent, then there is this recent work that studies the phase transition. Okay, so this is what has been done, and so also to mention a related model that also appeared in the physics literature. So this goes back to Tuner and Tu and Levine and Trappel and Cohen, and Ehrman and Ebeling. Okay, so there is a long list of names here. So here is a paper by my colleague Maria Darsonia, and Andrea Bertolzi, Lincoln Chase, and PRL, and a paper by Carillo, Darsonia, and myself. And then the subsequent work. So this is a popular topic to study this model. So basically, what this provides is a relaxation to there is a mechanism of relaxation to the velocity having length 1. So this term tells a particle that if it is too fast, then it needs to slow down, and if it is too slow, then it needs to to speed up. And this term vanishes when the velocity has length 1, and then there is an attractive repulsive interaction of the above type. Okay, so this is also related, and so for this model in particular, different types of dynamics have been observed and studied, and particular situations are. That if one arranges particles in a particular way, then one can observe particles milling. so going around in a circle, producing a sort of a vortex, in which every particle in this vortex moves with the same speed. So there is not constant angular speed. So it's really a state that is moving. One can sometimes observe two superimposed vertices moving in the opposite direction, which is something that has been observed in biological systems. So it's gained popularity because of that. So okay. So the aim of what I'm going to talk about is to formulate a kinetic mean field model for a three-zone model. So with repulsion, orientation, and attraction, which is completely deterministic. And so this is a system that basically that was used to simulate a migration of fish in the North Atlantic. So we want to treat the time discrete and time continuous versions with the same technique. So to prove the mean field limit in both cases, and so we are deriving a hydrodynamic model. So looking at the hyperbolic and so diffusive scalings. So there are different regimes that we can look at and study the conditions in which these models are valid. And so we want to compare the behavior of the particle system and the hydrodynamic model and see if you see that they match. Okay. So before we go on, so just to show the first slide. So basically, what I'm going to look at is the alignment function, which is say an indicator function of a ball, and the potential, which has so the force that I'm going to take will be purely repulsive. And I will put particles in a box of finite size to confine the system, so to make things work. But in principle, one could look at other settings of these type of models. Okay, so let me describe the approach of kinetic theory. So this goes back to the physicist Klimantovich in the 1960s. So you introduce a thing that is called the empirical measure, and the empirical measure is simply the way to reproduce your particle system by writing a sum of delta functions at positions xi and with velocities vi. And so writing this empirical measure, I mean that all the velocities here have length 1. So this naturally is a natural way to reproduce a particle system. Okay. So then, with the empirical measure, we can write the interaction as as a sort of a convolution of this kernel with this measure. Okay, so this term is the convolution with the potential. The velocity average, so the velocity average has v in it. So it's not really a convolution, but it is a certain average. Okay, so this is just this is just an identical transformation. It's a different way to write the interaction term. So by using this notation. Okay, and then so the dynamics for the empirical measure can be written in terms of this equation. So which is the governing equation for the evolution, which is simply this. So to find so we can treat our measure as a function on continuous functions. So its value at time t plus tau, so this mu evaluated on the test function phi, is computed from knowing the measure at the time t, and so using a test function which is x plus tau v and v bar. So basically using the rules for updating our particle system. Okay, so this is the starting point for all things that we do. So this equation makes sense for measures other than point particles. So basically, so in this equation we can just remove n and try the equation for mu, and so this procedure is called the mean field limit. So basically, so trying to make sense of this evolution for other measures than the point particles is the same as writing a Vladislav equation for a particle system. Okay, so the time continuous version of this is so if you have ODEs for the dynamics, then you can differentiate the equation on the previous slide with respect to tau, and then we obtain a weak form of this PDE, which is the Vladislav equation. Okay, so it comes so if f is computed as a certain average of the measure, then this is a nonlinear equation, which, well, shouldn't be called PDE because it has a non-local term. So with this formulation, we can so rather than tracking a system of n particles, we can look at the evolution of a measure, so which we can normalize to be a probability measure. And well, so the mathematical work for this so goes back to the 70s, to the work of Neunzert and so the Brushin, so who proved this in the case of Hamiltonian dynamics. And so there has been studies recently to do this for non-Hamiltonian dynamics. So Jose and many other people. So. So this is what we do for so the difference in this case is that we are looking at the distribution which are supported on the sphere. Okay, and informally what we want to prove is that as the initial data corresponding to the n particles approximates the initial data which is given by a certain smooth density, then the solution at time t converges to the corresponding solution of the Vladislav equation for t in a certain time interval. Okay, so this is essentially a statement of continuous dependence on the initial data for this equation. And so here is, well, so we can make this a theorem. So the condition in this theorem is that we have a result which is essentially local in time. So the things for the mean field limit work if you have dynamics which is Lipschitz continuous. So if you have an ODE with a Lipschitz continuous right inside, then it works. So in this case, well, there is an obvious problem with the equations that we have to normalize the velocity. So we have to divide by the norm of a vector. So we need to make sure that the norm of the vector is not zero, and it vanishes on a fairly complicated set. So the interesting thing is that when we run the dynamics in the computer, so it never becomes zero. But so to prove that it doesn't vanish doesn't seem to be easy. So but the statement that we can make is like this: for as long as this quantity, which is the norm of the interaction, remains positive, we have a solution. So we have a solution on a finite interval, and this interval will be infinite if this quantity never vanishes. Okay, so this is a finite time result. Okay, and well, so the techniques for this are known. So I won't talk much about this. So basically, so the technique of the proof is based on the optimal transport distance, and so you compare. So you think of two clouds of particles. So this is blue particles. So this is red particles. So say you want to compare the system with n particles with a system with m particles. So all the other parameters are the same. Okay. So then so the way you compare, you want to transfer mass from one group of particles to another group of particles. So there can be many ways to do this. For example, so we can come up with a particular way. So call this way a transportation plan from the blue dots to the red dots. And this constants here will satisfy certain normalization conditions. And then, so the distance is defined quite naturally as the way as well. So we can formulate the cost of transport, which is proportional to the distance between the psi I and I should have written eta j. So particle, the blue particle and the red particle. Okay, and then if we minimize over all possible aij, so this gives a certain distance. So this is for discrete measures, but the same thing can be done for general probability measures, and that defines a distance. And in fact, it makes the space of probability this makes the space of measures, signed measures, into norm space. So there are various ways to do this, and basically, so it is based on. So this is the principle, so to say. So you look at the evolution of an n particle system and an m particle system, and then so to compare one to the other, so you compare the trajectories. So in this way, then you apply the then you apply the Kantorovich distance to each term, and it's so it works in the way it should work. So it distributes. So in this way, and if we have a Lipschitz condition for the dynamical system, which is uniform in n, then the things work out. Okay, so that's this is the known technique. Okay.
Sorry, can you state again the result? Why do you have this constraint?
So why do we have?
The constraint in the statement of the theorem.
So the statement.
That's
So the statement of the theorem.
It in the proof.
Okay. So for the proof, this is just an idea of the proof. So the idea of the proof is that in order to be able to say that the dynamics of n particles is not very different from the dynamics of m particles on a certain time interval, we want to have a Lipschitz estimate for the right-hand side of the equation, which is uniform in n. Okay, and the way to express it is so if you write this right-hand side in terms of the measure, then so the right-hand side has to be Lipschitz continuous with respect to this measure. Okay, so we need Lipschitz continuity, which is uniform with respect to the number of particles. Okay, so we have this Lipschitz continuity, provided we don't divide by 0 in the dynamical system. So as long as we are able to control the norm of the interaction, we have the estimate for the Lipschitz constant, which is uniform in the number of particles. Okay. So then, so of course, since we are using the Gronwall argument, then so this is the convergence for the convergence works for any finite time interval, but the rate of convergence deteriorates as time increases. So it is short time or long time dependent on the dynamics. So if the dynamics works in such a way that the interaction never vanishes, and so far in all the simulations that we ran, it never vanished. So then it is global. But we cannot we cannot describe it explicitly. Well, actually, in simple examples, so in particular, if you look at particles in which so the velocity is computed just by averaging velocities, so mu qi. So if you just so normalize. So if you look at the situation when b equals 0, so then if you start with initial distribution of all particles within within an angle of less than pi, then everything will remain within this angle, and then we are guaranteed that the dynamics will be extended for all time. So if we add the interaction, then it becomes difficult. So we can say that if the interaction is small, then then this will persist for a certain finite interval. But it seems to be difficult to describe the conditions so that the dynamics is extendable for arbitrarily long time. But again, I mean, so on practical terms, it doesn't seem to be an issue for the systems that we are modeling for any kind of initial data. But well, which is not a proof that there isn't a pathological set of initial data for which it wouldn't work. Okay. So Okay, so the idea of the hydrodynamic limit is the following. So we look at the system of n particles. So radius of interaction is epsilon, and the time step is tau. So the hyperbolic scaling would be to let epsilon to 0. So to make well, we are making the radius of interaction smaller, and making the time step proportionally smaller, so that epsilon over tau goes to a finite limit. And then so epsilon to the d times n, which is the number of particles in the interaction zone, remains constant. So this is the classical setting for a hydrodynamic limit. So this is this type of scaling is reasonable on physical grounds. So well, basically it could be formulated so that as n increases, the size of the system grows proportional to the number of particles. And so this was actually used in this modeling paper to match the parameters that were used in the simulation to the biologically reasonable values. So the simulation was done with a few tens of thousands of particles, and so they were trying to estimate the path of the migration of the fish with the number of fish in the system of the order of 10 to the 9. And so by using this type of scaling, so they actually computed that the values that they were using in the simulation were matching the biologically relevant values. So that's just an interesting aspect. So another possible regime that we could be interested in is letting epsilon to 0 and tau to 0, so that epsilon square over tau goes to lambda, so finite constant, and that would be a diffusive scaling. So basically looking at a longer time scale. But for this we have to scale the force proportionally, so that so with the finite force we'll see things in the hyperbolic scaling. And so then, well, to formulate the problem for the hydrodynamic limit, we could do it in this way. So consider the empirical measure for n particles with fixed values of epsilon and tau for a system that is contained in the fixed volume, so of volume L to the d. And then, in the hyperbolic scaling, so let epsilon go to 0 at this rate, so n to the minus 1 over d, or say proportional to this, and epsilon over tau goes to a limit lambda. Then the question is, what happens to the limit of mu epsilon n t? So say the initial value approximates something nice. So start with a nice and smooth density rho naught and velocity v naught, and so let's take the initial data in this form. So what can we say about the limiting measure in the limit? Okay, so this problem seems to be difficult, and so the way to address it that we are hoping would produce a meaningful result is to sort of first let n go to infinity, and then hoping that nothing bad will happen. So, I mean, we have the mean field limit to confirm that on a certain time interval things do not change drastically, but this is a belief. And then so let epsilon and tau go to 0 at this rate and see what happens in the equations. Okay, and well, so we cannot prove a theorem, so it's just seems to be a hard problem to prove it. But there are some calculations, and we can derive equations, and I'll show some results. So basically, this is a heuristic part. So we write the equation for the evolution of the measure. So the measure at time t plus tau, computed at the function phi, is this. So then, so we can write it as in the form with a finite difference. So divide by tau. So then, so this is something that resembles the derivative of mu evaluated at phi. And well, so here, so acting optimistically, we can put the limit inside, and so hope that everything works. And we see that in order to make sense of the right-hand side, we need to ask that v bar minus v. So v is the velocity computed by the interaction, so which is the average. So divided by tau has a finite limit. So informally, this means that in the limit we expect the velocities to So whenever mu t is not 0, we expect the velocities to be equal their local averages. Okay. So we may expect that a solution of this form would be a reasonable approximation in this case. Again, so this is something that is not easy to justify, but this is a belief, which may be true in some cases and not true in other cases. Okay, so then if we compute the velocity obtained by computing the interaction, so this is the velocity, and then expanding into powers of epsilon, so we can find formally that the zero order term is so this j. So j is the average. Well, so that's the flux of the local flux of particles, just the first moment of mu. And rho is the local density. So then the first order term is the gradient of rho, and then higher order terms is the Laplacian of j. Okay, so with this type of formal expansion, so we can write v bar as an expansion with the first order, second order, and so on. Okay, and then so basically, so the procedure works in this way. So we take this equation, well, either this form or this form. So in this form, we can write the expansion into a Taylor series in tau, and so here we write the expansion into a Taylor series of the function phi, and so use the expression for so the most crucial part is this v bar. So if you write everything out and compute the terms with equal powers of epsilon, then and assume that epsilon is proportional to tau, then this is what is coming out. So the first equation is not surprising. So this is just a continuity equation. So the second equation has the gradient, gradient of rho projected in the direction perpendicular to u. And again, so this is in the hydrodynamic limit we get the pressure that is simply proportional to the density. So the force is taken into account by saying that the particles react to the gradient rather than to the force. So we can compute the constant lambda here, which is the ratio of the integral of v and the integral of k. Okay, and again, so this works for the time discrete problem as well as the time continuous problem. So at least at this level. So in the diffusive scaling, so if you remove the attractive repulsive interaction, so if you say that the things only align, then so this type of approach gives us a viscosity type term, which is projected again into the direction perpendicular to the velocity. So it's like this. Okay, and so basically, so this is as much as we can say with at this point. So the current work that we are doing, so we're comparing the results with some of the numerical simulations that we did. So I'll show how the things look like. So basically, so this is yes.
So you have a non-conservative term that appears on the first slide.
Right.
And this is due to which part? Where does this come from in the
Okay.
dimensional projection?
So that's a good question. So right. So this is so the non-conservative part of the system is here in this projection part. So the way this projection comes out is also here. So basically, so when we compute the velocity. Okay, so
Well, let me ask it a little bit differently. Okay, if you view that as a macroscopic equation, it's a very bad equation to study. Let's say, does the microscopic model, does it offer you a perspective on how to handle the non-conservative term?
Well, so there are some ideas about this. Basically, the limiting equation is a hyperbolic system, which is non-conservative. So the question that is posed is so how to handle discontinuities in solutions for this system. Well, so first of all, I mean, so all the hope for the derivation is in the well. First of all, we assume that the solution that the solution of this microscopic system is smooth on a certain time interval, and so the best hope that we have is to prove that on this interval the particle system approximates the continuum model. Okay.
The next
But-
term of the asymptotics that you left out, what is it? Have you
So-
considered that?
Basically, the way this projection comes out is like this. So if you compute the velocity, then the velocity, if you compute the velocity which is the interaction, so then this is the average velocity minus so the first order term is proportional to the gradient of rho. So if you divide by the norm of the velocity, which is rho, it's norm of the flux, which is rho, it's like this. And then, so if we expand, this 1 over the square root, then out of the expansion, we get the projection. So basically, so computing these terms, so we find that the term, well, the first order term is projected into the direction perpendicular to you, and so will be the higher order terms. So this projection just comes out of the expansion.
It's related to the fact that the velocity has to be over modulus 1 in the practical system.
So this is related to the fact that the velocities are 1 in the absolute value. And again, in this situations that we are studying, so since our solutions are monokinetic measures, then so the macroscopic velocity is also 1 in the absolute value. Okay, then so how to handle the non-conservative term? Well, so one approach is that works in the numerics, and so this is what was studied by Laurent Navarrete and so Sebastian Moch. Is that if you do the idea of relaxation, so the relaxation works in a similar way to the model that I was describing. So if you don't insist on all particles having velocity 1, but you say that there is a mechanism that drives all the velocities to speed 1. Well, then computing a relaxation scheme for this non-conservative model seems to match the results that one gets with particles for discontinuous solutions. But this is again, so this is somewhat recent, and so there is no rigorous justification for this procedure. It seems like a difficult problem. So part of the interest to this model is so how to handle discontinuous solutions for this system. Well, so let me show. I hope I can show this. Just to illustrate how the dynamics evolves. I hope you are able to see how this works. So this is with a relatively small number of particles. The only mechanism is orientation. So we start with a completely disordered state, and then so particles find each other. So they form groups. So the groups evolve on a larger scale. So again, so this is a problem in which we don't have a mechanism for the particles to keep distance away from each other. So they form structures on the microscopic scale. So then, so this is a similar situation with a slightly larger number of particles. So that's again, so just a pure alignment. So they form microscopic structures, which seem to evolve in an interesting way. But again, so that's they do not fill the whole domain. So this is if we add a repulsion mechanism, then things becomes more smooth. So there is a tendency similar to what was observed before. So they form groups, but then so there is a certain period where we have smooth evolution of density, and so here things are really hard to see. But basically, so we see waves on the microscopic scale that are that we can.
Layer. There is the formation of a layer. I cannot see very well.
No, it's so unfortunately that's just this is just on the screen.
Okay.
So,
Just understand.
I can show you there is absolutely no So it's a smooth carpet.
Is it in vertical direction?
Yes. And what is the here is a shock problem. So in order to compare with the model situation, so we want to take one-dimensional data. So here is so the particle system is still two-dimensional, but the initial distribution was a discontinuity in the middle. So this is a solution of a certain Riemann problem. Okay, so and again, so it's not easy to see in the movie, but so let me show what happens in the one-dimensional picture. So this is the same type of initial data. It takes some time to load the graphics. Unfortunately, it worked. I tested it. Okay, just a second. So that's the thing. Start again. Okay, so we start with something that looks like a. So this is a particular case of a Riemann problem. So there is I didn't try to match it to Rankine-Hugoniot conditions. So there is an intermediate state which resembles a shock for a while. So there is a sort of a rarefaction way of going the other way. And then so after so this is no longer Riemann problem. So then the two waves meet. It just goes. So it's I hope this picture shows that this system actually displays some behavior which is similar to the hyperbolic system, so with waves interacting in a nonlinear fashion.
Is there any more questions or comments?
Since you mentioned this lineup with, like the swarming, the migration patterns essentially of the fish in Iceland, I can't stop myself asking a little bit the background, because like if you live for long enough in the UK, you come across these amazing documentaries of Söderberg Edinburgh, and there you can see, for instance, these massive swarms of sardines, for instance, 10 to the 9, 10 to the 10 individuals. They're essentially the sort of tooth type of things. If they're undisturbed, they try to follow plankton, which they feed on. And the plankton usually gets trapped where you have sea currents actually crashing each other. And in these layers between sea currents, there is typically a higher concentration of planktons, and that's where the fish essentially want to follow. And this is in time scales and let's say in length scales, where I would think that would be the dominant effect, that the actual swarming of the 10 to the 9 individual doesn't really change it very much. On the other hand, if like where you have sardines, you have also the tuna and the dolphins which try to feed off them. So these beautiful meals which you actually see, that you see only if the little fish already realize, that there are the dolphins coming, for instance, and they line up frantically and make these meals until they really come. And then it's all chaos, because you have, like hundreds of prey fish getting into the swarm and whatever. Usually the swarm ends up being totally eaten. So then it's also not so relevant anymore for, comparing, like the swarming with the experiment. So I didn't clearly get the point where the swarming is really important if you try to simulate migration.
So there is no, so in the migration there is no swarming. So the migration is a comparatively, so it's not so. It's not so exciting. So they just so there are huge masses of fish, and basically what people try to see is the path of the migration. So it's not the small structures. It's not the life of groups of hundreds and thousands of fish. It's really the large scale. So because there is interesting dynamics that is happening on a scale of several hundreds of hundreds of individuals. And so for this type of in the migration problem, what really matters is what really mattered in order to capture the path of the migration is to take into account the interaction with the environment. So the fish prefer to stay in a certain range of temperatures. So they prefer. So they follow the current in a certain way, and that was basically how it worked. It's not the complicated dynamics that makes the migration. It's just taking into account the interaction with the environment in the right way. But in order to do this, you need to reproduce this in a certain way, and the particle seems to be a good way to do this. So there has been studies to do this with reaction diffusion equations, and it wasn't so successful. So the particle model was better in capturing this aspect.